Hi, can you hear me? Okay, great. It's only 4 people. Okay, we're starting now. Let's see. And notice that all of a sudden we have some questions about the assignment at this late date. Circuit in question 5.5. Yeah, we'll talk about that today. Reading for assignment 2. Is it difficult to find? Maybe I shouldn't put it in the header. Okay. Any questions or? Hope you had a good reading week. It's always left a little bit unspecified what exactly you're supposed to read. Did anyone read anything good?
Read a lot of one of my textbooks.
Read some textbooks?
This is for quantum field theory.
What did you read?
Reading about renormalization.
So if you're taking quantum field theory, why are you taking this class?
For the groups.
I see.
Mostly. And to see quantum from a different point of view than what is usually taught in physics.
Wow, we have someone with massive robots behind them. It's a nice background.
It's the Tony Stark studio.
Oh, I see. So that means that would make you Tony Stark then.
No, just hanging out here.
Oh, right. Oh, you're just
like
hanging out in the
robots.
studio. Right. James, you seem to have a huge whiteboard behind you. Is that right?
No, it's just an empty wall.
Oh, it's an empty wall. Oh,
I wish I had a whiteboard that big.
Just because there's a top and bottom bar.
Yeah.
Looks like it. I see. Well, it's a nice day in Toronto. Is there anyone who's not in Toronto right now? No, everyone's in Toronto.
I almost feels like spring. I was very surprised going out.
Well, there was that. I'm very disappointed with this. There's this rodent in Northern Ontario. Well, they call it Northern Ontario, but it's actually not Northern. It's just at the top of the Bruce Peninsula. There's this groundhog in a small town, and that's the Canadian replacement for the American groundhog. That's supposed to foretell the arrival of spring. And this idiotic Canadian groundhog said that we were going to have an extremely early spring. Wyerton Willie. He's a national embarrassment. But at least the light is spring-like. So the light is the most important thing.
Shouldn't the light be constant every year? Because it's just determined by the angle.
But what do you think?
Well, probably.
You think the light is only determined by the angle of the Earth?
Well,
What about
probably
clouds?
Yeah, I think Karayun has a little bit of a good point.
Fair.
There was a couple of years back in the olden days when the sun didn't come out at all.
Yeah, for the past 2 years, I think I haven't seen the sun that often in the wintertime. This is kind of nice.
Yeah, definitely. Actually, it used to be. I haven't lived in Toronto for that long, but the people who lived here before me, like before 10 years ago, they said that the winters in Toronto used to be very bright, always very bright, very sunny and very bright. But it's gotten a lot more dark. Or yeah, I don't really know. Maybe it's not true. The weather report, do they include lux? They should include some measure of light. I don't know if they do.
Wouldn't that be like the UV index?
I guess so. But the clouds, sometimes you have a lot of clouds and the UV index is still high.
And vice versa. Sometimes the sun is out, but the UV index isn't super high.
Oh yeah. Right. So yeah, the weather reports, they're only marginally better than Mr. Willie there.
They should tell us how strong or weak the magnetic field is every day.
Oh yeah, that's highly useful. Yeah. For those, it's kind of amazing. There are some creatures, they have some kind of ferromagnets embedded in them, and they can tell the direction of the magnetic field. But we don't know whether humans have this feature. We might actually have the ability, but we may not be aware of it. I wonder if we do. We have these very tiny crystals in our ear that are used for something. I can't remember. Calcium crystals. So maybe we have a ferromagnet somewhere. They keep finding new pieces of anatomy in the human body, even now, like in 2021. It's inspirational, I think. Imagine if you could discover a new part, a new feature. Well, we're the user of some software that we don't even know like what the full feature set is.
At least there's no pop-ups though.
Yeah. Well, is that true? Actually, I was explaining to my students, we had a large group in my office, and this was about 6 months before the pandemic, where I was, sometimes I do this for my grad students, where we have a big meeting and I put on a talk from a famous mathematician, and we basically watch it together. And whenever there's something that they don't understand, I pause the video and explain what the person is saying. So we basically, it's like a running commentary on a math talk, like a running analysis of the math talk. And so this thing usually takes a very long time. Like 1 hour of math talk usually gets expanded to 4 hours of explanation because of how dense they usually are. And about 3 hours in, I started to see flashing lights in one of my eyes and a dark spot in the other eye. And so I thought I was having a stroke. So I said, I told them to keep watching the video, and I ran out of my office to the bathroom to do the stroke check. This is not very wise. I'm not, but then, so I realized I wasn't having a stroke, but something else really bad must be happening. And I decided to go to the emergency room, which the fastest way to get from my office to the emergency room, because it's U of T, right? I mean, the hospital is right there. So you can try to get a cab, or you can try to get someone to drive you, but actually the fastest way is just to run there as quickly as you can. So I ran as fast as I could with these flashing lights in my eyes and got to the emergency room. and they said once they did a few tests, and they said you're having a textbook case of migraine headache with aura with no pain. So there's no headache, actually. It's just a migraine with aura, with flashing lights. And I only had it once, never had it again. But actually, when I got back, they were all gone. They didn't even finish watching the video. Incredible.
Maybe your ferromagnets were out of order.
Yeah, something was wrong. There was a pop-up anyway. That's the reason I told that story. This weird pop-up. There's not enough people here. Only 21 people. Oh no, actually, sorry. That is enough people. Okay, let's start. So we don't have much time today, but I'll cover two things. One, I'll answer the question about the circuit diagram. But I'll do that after I finish this. We were almost done with this little example. So let me just finish that. So let's remember where we were at. So we were on a configuration space, which is the circle S1. And therefore the classical phase space is the cotangent of S1, which to each point gives the dual of the tangent space. So that means that for each point of the circle, we have a one-dimensional real vector space, and that gives you a cylinder if you put it all together. And this is supposed to be a free particle, which means that the only component of the the only component of the Hamiltonian is the kinetic energy. There's no potential energy. And so the kinetic energy is just the squared norm of the momentum, which gives a quadratic function on each cotangent space. Each cotangent space has a quadratic function on it, which vanishes at 0 and which grows as the further you get away. You know, the bigger the momentum is, the bigger is this kinetic energy function. And then in the classical system, you know, in the classical mechanics, this function generates a time evolution. And the way that it does that is by giving a Hamiltonian vector field. And I drew the vector field in green. You can see that it's basically turning. In other words, it's moving the position at a constant rate, depending on how big the energy is. If the energy is very large, then that gives a lot of momentum, and you get very quick motion. If the energy, I'm sorry. The energy is a function on the phase space, but depending on what the initial momentum is, if your initial momentum is very high, then it will just conserve, and it will. You can see right away why does the time evolution conserve momentum? Well, because this function, which generates the time flow, Poisson commutes, right, with the momentum function, because h is just a power of p, right? So if I just briefly, just kind of to refresh your memory, right? If I want to compute, let's say p 1/2 p squared, right? This bracket, it behaves according to the Leibniz rule in each argument, right? So this is going to give 1/2 of, it's going to give basically pp, right? Because this is basically differentiating this function. So the way that it differentiates is that this operator, it brings down a 2, that cancels out the 1/2, and then so let me write this out in detail, sorry. So you'll get 2 times 1/2 times p times p bracket p. Just as you would do if you were differentiating with respect to a vector field, you would say, well, it's like 2 times 1/2 times p times the derivative of p. And so that's what is happening. And then this is skew symmetric, so this is 0. So you can see that p it commutes with h, and therefore p will be conserved under the time flow, under the flow of h. And so momentum is conserved, as you would expect for a free particle, and that momentum is just generating circular motion at a constant speed, either at speed, at a positive or negative speed, depending on what the initial speed is. And the point was that depending on the level, depending on the initial momentum that you provide the particle with, you could be at any level of this value of the Hamiltonian. So you could be at 0, you could be at 1, you could be at 1/2, or you could be at value pi. You can put as much energy into that circle as you want. It just will affect how fast the particle is moving. So you could think of that little thing as a perfect sink of energy. You could dump energy, no matter how much energy you have, no matter what quantity, you can dump it into that circle, and it'll just make that particle spin faster and faster. Now, for the quantum version, we need to consider, just as we did for the finite sets, the functions, the wave functions on the configuration space. That gives us a vector space, and then we complete it using the inner product, the natural inner product of complex valued functions, where we just multiply and integrate with a little complex conjugation there to make it an inner product in the usual sense, like on a complex vector space. And then once we have our Hilbert space, once we have our vector space with a Hermitian inner product, we need, in order to define the quantum system, we need the Hamiltonian operator. The Hamiltonian operator is a self-adjoint operator. And remember that our approach, kind of the way that we're going to cleverly get self-adjoint operators is that we're going to remember that the difference between a self-adjoint and a skew-adjoint operator is just multiplication by I. And skew-adjoint operators have a very nice mathematical meaning, which is that they are Lie algebra elements whose exponentials give symmetries, give unitary operators, which are symmetries of the quantum system. So what we're looking for, ideally, the easiest way to get ourselves a Hamiltonian is to find a symmetry and to use that symmetry, multiply by I, get a self-adjoint operator, and then we're rolling. We could look for the eigenvalues and so on. So the obvious, there's two obvious observables, self-adjoint operators, that we have available. One of them comes from the rotation action on the circle. That is an argument shift. It induces an argument shift on the wave function. So if you rotate the circle and you drag along the wave function, that will be a unitary operation that doesn't change the norm squared of the function. And we call that phi star theta. And here I explained that it is unitary, so it preserves the inner product. And the derivative of this thing is going to be just the usual derivative on the circle, which I write as d by d theta. And we see that this is skew adjoint. So we found our Lie algebra element. It is indeed the vector field on the circle, which rotates at a constant speed if you integrate it. And then if we multiply by minus I, we get a self-adjoint operator, and that is called the momentum operator. So we've got our first observable, and what we could do is just by analogy with the classical case, we could produce something like a kinetic energy by squaring this thing. So we take this self-adjoint operator and we square it. Now, no one said that self-adjoint operators form an algebra. You can't necessarily multiply two self-adjoint operators and expect to get a self-adjoint operator, right? I mean, if I take A and B, if each of them is self-adjoint, and if I take the adjoint, this will be B star A star. So this is not the same as AB. This will be the same as BA, which is not the same as AB. So So there's no one ever said that you can multiply self-adjoint operators, but you can multiply a self-adjoint operator with itself. Then it works. As long as the self-adjoint operators commute, you can multiply them and get another self-adjoint operator, and that's what we do. So we take 1/2 p squared, and we get this operator, which will play the role of the kinetic energy. And we're going to use it as the Hamiltonian. So you could say, well, why don't you use P as the Hamiltonian? Well, there's no reason, mathematically speaking, we could consider any operator to be the Hamiltonian, really. But this one's a good one, and it's the one that if you do a semi-classical analysis, so if you introduce the h bar and you try to take a limit as h bar goes to 0, then you'll see that this is the right choice in order to recover classical mechanics of a free particle on the circle. But let's not go into that right now. We might go into that later at the end of the course. For now, we're just defining this to be the Hamiltonian. Okay, and then what happens when we do that? Well, okay, so actually, let me just keep the mass in just to emphasize the connection with classical mechanics. I'm going to take 1/2m times p hat squared. Okay, and this is going to be minus 1/2m del squared by del theta squared. So we're on the circle. We have a coordinate theta, which is not a real coordinate. It's only valid up to the understanding that when theta is 2 pi, we should consider that to be equal to theta equals 0. So it's not a true coordinate, but never mind, we're used to that. This operator, however, is perfectly well defined. If you send theta to theta plus 2 pi, this doesn't change. So what is this? Well, this is nothing but the Laplacian on the circle. So it's like, when you take grad squared, to define your Laplacian, this is exactly what it is. It's the second derivative. And now what we want to do is we want to solve the time evolution of the system. So the Schrodinger evolution is basically telling us that the time derivative is given by the Hamiltonian. And let me just continue to assume that h bar is equal to 1. And this is going to be minus h. Okay, so again, I just want to emphasize this. So this is the abstract Schrodinger time evolution, right? Where psi is a vector in the state space, is a vector in the quantum mechanical Hilbert space. So in this case, psi is viewed as a function on the circle, because that happens to be what our vector space is. Unlike, let's say, the qubit, which wasn't really a function on anything, that was just a vector space, a two-dimensional complex vector space. Here, this psi is a vector which has a meaning as a function on a classical space. And so this operator, even better, this operator is now an operator on those functions. And even better than that, it's a differential operator. There's no reason why an operator on the Hilbert space of functions should be a differential operator. There's plenty of operators which are not differential operators, but this one is, and we get this equation like that, which I'm again going to assume h bar is equal to 1. So we get an equation which says that I del t psi is equal to minus 1/2m del theta squared psi. Okay, and this is basically saying that the time derivative of the function proceeds according to the second spatial derivative of the function, and this is very familiar. It's almost exactly what you see in the wave equation or in the heat equation. sorry, not the wave equation, but the heat equation. So this is very similar to the heat equation. The heat equation says that the time derivative, like if you have a local maximum, right? If you have a local maximum, then according to the flow of heat, that should smoothen out. So that means that the time derivative of something that has a local maximum should be negative, right? And something that has a local minimum, the time derivative should be positive. So if the second derivative is negative, then we expect that the time derivative is negative. So, if you just multiply, so the main difference is basically this I in front. So this is similar to the heat equation, but with I on the left-hand side. Okay, so you could, so what some people do is they will complexify all the coordinates. They'll complexify t, and then once you complexify t and theta and what have you, then the difference between the heat and the Schrodinger equation kind of disappears. But anyway, this is a different equation. Let me just proceed, and then I'll get to Christopher's question. So how do we solve this? Well, the good thing about this Hamiltonian is that this Hamiltonian operator on functions, it has eigenvalues and eigenstates, and it turns out that it has so many of these eigenstates that they form a Fourier basis for all functions on the circle. So that means that what we can do, this is this typical strategy. So first part of the strategy is find the eigenstates of the Hamiltonian operator, and that's pretty easy to do. We're going to look at h psi is equal to e psi for e. That's going to be h hat is a self-adjoint operator, so its eigenvalues must be real. So we're going to find its spectrum. So the question is, what is the spectrum? And what are the vectors that contribute to that spectrum? So to solve this, we are just solving the equation minus 1 over 2m del theta squared psi is equal to e psi. And you know that you can use exponentials to solve this. So psi, well, okay, so this is the key point, is that the solution to this equation, you could say that they're kind of like cos and sine. So they're sinusoidal functions. And these sinusoidal functions, they need to be defined on the circle. And so that means that from 0 to 2 pi, they must be 2 pi periodic. So we get 2 pi periodic sinusoidal functions as the solutions. And let's see, where did I put my solutions? Yeah, so if I take one of these sinusoidal functions, what will it look like? E to the I n theta, where n is an integer. These are the 2 pi periodic solutions. Let me compute the solution. So psi double prime is exactly minus n squared times psi. Okay, and so this means that I've got my eigenvalue. So that means that the energy times 2 pi, times 2m minus 2m e is equal to minus n squared. Okay, so that means that that the energy, the possible energies, are going to be n squared over 2m. Okay, and here, like, this is the reason, Like, this is the reason why the subject is called quantum mechanics. It's because this, the possible values of the Hamiltonian, the possible spectrum of the Hamiltonian, unlike the classical case, is discrete. They're quantized. Okay. So we have quantized quantization of possible measured observables. Okay. And then after the first step is done, we go to the second step. So now we take psi and we expand it in terms of these Fourier modes. So we write it as a sum, sorry, at time 0. We take our initial state and we expand it out in terms of the integer that parameterizes the solutions, and then we know how this thing varies in time, because we know how each one of these things develops in time. So we're just going to get an, and then psi n is an eigenstate, and so it just gets multiplied by its energy. So this here is the time evolution of an eigenstate of H. And notice that it's only being multiplied by a phase. And so therefore the physical state is actually not changing for an eigenstate. So these are these states, that's why these states, so since the physical state psi n is unchanged in time, the H eigenstates are sometimes called stationary states. It's true that they're being multiplied by a phase, but remember that phase is unphysical. But the important thing is that when you have a sum of several of these, then each one of them will be multiplied by a different phase. And so while the individual phases do not matter for stationary states, when you have a sum, then those phases really matter a lot. They will change the linear combination very dramatically. And anyway, this is what your time evolution looks like. Okay, now this is what you would call a complete analytic solution of the quantum system. It's basically telling you that any function in L2 of the circle evolves, any wave function at all evolves according to this law. You take the Fourier transform, right? So we start off with L2 functions on the circle with complex coefficients. We're using the Fourier transform as a tool. We didn't need to do it, but it was very helpful. So we use the Fourier transform to express this in terms of L2 on the integers. We take psi of 0 and we map it to this sequence A sub n, n in Z. Okay, this is a unitary isomorphism. That's what they should teach you in any analysis course. If they don't teach you that in analysis, then I don't know why they're teaching the class. So the Fourier transform gives a unitary isomorphism between these two Hilbert spaces. And it's just useful because this Fourier decomposition is using the Hamiltonian for the free particle. You could have used a different Hamiltonian and gotten a different Fourier transformation. And that Fourier decomposition would not be useful for this problem, just because that Hamiltonian is irrelevant here. Okay, so you should not think that the Fourier transform is somehow important in some fundamental way in quantum mechanics. No, the reason that it's important is because the Fourier transform on the circle is literally expanding in terms of energy eigenstates for the free particle. And so of course it's going to be helpful for the study of the particle, quantum particle on a line or on the circle. Okay, questions. So this is a kind of complete solution of the free particle on the circle.
I have a question.
Yeah.
Going back to something you said at the beginning.
Yeah.
Maybe I'm forgetting something, but so you're saying like when looking for observables, we'll look for like a UN symmetry because the Lie algebra of UN is going to be skew-adjoint elements, and then we can multiply by I to get a self-adjoint element.
Yeah.
But so does our quantum system always, like what if we don't have a UN symmetry? So the Lie algebra of our symmetry group is not the skew-adjoint elements. Like where do we construct our observables from?
Yeah, I mean, you know, it's a good question. You need to construct them somehow. So you need to have some method of obtaining that self-adjoint operator. Now, what I'm saying, and that's one of the good things about the textbook that I recommended, the Voigt book, is that in reality, most of the time when you get these self-adjoint operators, they come from some kind of a symmetry. They don't have to be necessarily a symmetry of the system they don't necessarily have to be like, for example, in this case, right, we didn't actually use the momentum in the description of the quantum system. We used the square of the momentum. So what you see, what's happening is that there's some kind of fundamental symmetry corresponding to rotation. And then we're going to use that as a backbone to build other observables via some algebraic procedure. In this case, that algebraic procedure is the squaring it. Okay, but there are more sophisticated versions of that. And then we're going to build something like that. Or you could imagine taking you know, other polynomial functions of the fundamental observables that come from symmetries. So you see what I'm saying? Like you might have some symmetries, but you shouldn't think that we're going to build a quantum system that necessarily has those symmetries, because we're not necessarily using those as the Hamiltonian. We're using something that is derived from those symmetries that, okay, fine. You can then say, yada, yada, yada. What if you don't have any symmetries at all to begin with? What if you have nothing? Well, if you really have nothing, then you can't build your observable. I'm sorry. You need something to build the observable. So that's something might be, rather than a symmetry, it might be something which is associated to a small part of the system, and the system might be repetitive, right? So it's not that the system is symmetrical. It's more that the system is built out of many small parts, and that if that's the case, then you can take a Hamiltonian. You can take let's say that small part has a symmetry. Therefore, you get an observable there, and then you can tensor that up and produce a huge observable for the conjoined system, even though that conjoined system doesn't have that symmetry. You know what I'm saying? So you have to have tricks in order to build these observables, and you cannot build it out of nothing. There has to be some kind of aspect to it. And the funny thing is that is not really part of the axioms of quantum mechanics. That's more of like examples. It's more about how do you actually build quantum systems. You need, you know, the true answer is that you should just be given a Hilbert space, and you should be given the Hamiltonian, and you know, that's it. I mean, what I'm trying to do is I'm trying to give you some kind of methods for producing more and more examples of this system. So we're going to see more examples. Like this one is a prototype for a large family of examples, and then the hydrogen atom, which is coming up soon, that's another prototype for a different type of example. And there's a bunch of these prototypes that you learn in quantum mechanics, and that's basically it. There's no, there's only a few known ways of producing quantum systems, and that's how you proceed. Okay, so there's one other thing that I need to mention about this system. This system already demonstrates something really cool, which can happen. What are the possible energies? Let's assume the mass is 1. Let's assume let's assume the mass is 1/2. What are the possible energies? They are n squared, right? So okay, so so this tells this says that we have for n equals 0, what does that look like? What does that stationary state look like? It just looks like just psi equals 1. So it's a constant wave function. That's perfectly valid. It has no energy, and it corresponds to a particle. What's a zero energy state in the free particle on the circle? It would be a particle located at a specific point and which is not moving in time, right? So this is quite a contrast, that in the classical system, the zero energy state consists of a particle at one point, but at which point? Remember that the phase space had zero energies. The zero energy set consists of all the points for which P is equal to 0. So there was an infinite number of zero energy states. So in the classical system, there exists an infinite number of distinct zero energy states. Whereas in this case, there's exactly one zero energy state. That if the energy is 0, that means it has to be a zero eigenstate of this operator, which means that the derivative must be 0. So there's only one function in L2 whose derivative is 0 like that. It's the constant function. So there's only one function which is a solution to this differential equation, right? Which is the 0 function. So we have a unique state, and I'm going to denote that by drawing a single dot. So there's a single quantum mechanical zero energy state. Okay.
Maybe this is a dumb question, but why can't you take different constant functions? Just as you have different points on the circle.
Does anyone have an answer to that? Why can you not take different multiples of the constant function?
Or modding out by multiples of unit or multiples of...
It's just a phase. A phase.
Oh, right. Okay.
Yeah. Okay, so what is this state? What is this state? What should it be called? The wave function is on the... So you could say, well, how do you describe this state? Well, what does it mean to describe a state? Here, we only have one observable. We can describe its energy. Well, okay, secretly, there is another observable, the momentum. And the momentum applied to this, momentum is minus I d by d theta. It has 0 momentum. So I can describe it as having 0 energy. I can also describe it as having 0 momentum. And then you might ask, well, where is it located? Where is this particle located? Where is the state located? What about if I measure the position? Well, for that, I need the position observable, and I have not introduced it yet. Okay, so we don't have a position observable yet. We don't have any other observable yet, so there's nothing else for me to say about this state. It's okay, but it's the unique 0 energy state. So when you look around, like if your universe was the circle, right? What would this state? What would this state be? How would you describe this state as a state of your universe?
the absence of states, like the absence
Well,
of.
no, not the absence of states. It's a state.
I mean, like the vacuum, I guess.
The vacuum. This is what physicists call the vacuum state. Okay. When they say the vacuum state, what they are saying is that in the Hilbert space of possible states of the universe, there is a single state. They're making a claim that it's unique. Okay. And the claim is that it has zero energy or has the lowest possible energy. Okay. And they're making a claim that it's a unique state. And this is a system that has a vacuum. So this is called the vacuum state. And it's unique. When physicists talk about, systems that do not have a unique vacuum, they talk about vacua. And they ask the question, what vacuum is our universe actually in? I mean, I think it's a funny question. They talk about, if there's many different vacua, then you might say, well, okay, you could be in, because everything likes to go to the lowest energy state, to populate the low-lying states, the low-hanging fruit. Then you might say, well, which low-hanging fruit am I in? Am I in this local minimum, or am I this local minimum? Which vacuum am I in? Of course, the answer is that the universe is not in the vacuum state. It's never in the vacuum state. There's always something going on. And so, but nevertheless, the idea is, where are we close? Are we close to this vacuum or to this vacuum? So in fact, there might be multiple, when we talk about multiple universes, actually there might be just one universe, but there might be multiple vacua that the universe might preferentially be in, or we might be in some kind of linear combination of vacuum states. Anyway, for this universe here, there's a single vacuum. So, that's where if you meditate, that's where you go to that vacuum. Okay, but then what about the next state? The next state has energy 1. Okay. Oh, great. What is this called? What is this? What is this called? This region between 0 and 1. No one knows? Physicists talk about it ad nauseum. There's even $1 million math question devoted to this question.
Mass gap?
That's the mass gap. Okay. The mass gap is really a property of a quantum system, which says that between the vacuum and any other state, there is a buffer zone where no energy states are allowed. No states of any kind are permitted in that gap. Okay, and for a system to have a mass gap, right? I mean, this system has a mass gap, but the classical system does not have a mass gap. Okay, any amount of energy that you want, 1/1,000,000 energy, that's perfectly okay for the particle on the circle. But for the quantum particle on the circle, there is a mass gap, and that means that this is like parents after their first child. After the first child, the parents are in the vacuum, and the child could cry and scream and kick, and they couldn't be bothered. Nothing affects them. There's a mass gap. Okay, there could be all kinds of electromagnetic radiation of low energy going around, but this particle will never absorb it because the energy is too low. It has no capability of absorbing that energy whatsoever. It's completely impossible because it has nowhere to go. Only once that laser gets to a high enough frequency so that it matches the mass gap will it be possible for the particle to absorb that energy. Well, assuming that it has a charge, because if it doesn't have a charge, then it's living in a completely different universe. It doesn't have electromagnetic power unless it has charge. Okay, so anyway, that's the mass gap. There's something inaccurate, badly inaccurate about this picture so far. What is it? There's something extremely wrong about the picture here. Why is this a bad picture?
There's only 1 point.
Why? How
No,
many
true.
points should there be?
2, I'm
Which
guessing.
corresponding to what states?
N minus 1 and I mean n, yeah. I don't know. I know
Corresponding
there
to
should
which
be 2
states?
because
These are our states. These are our stationary states. So if you measure the energy of your state, it's going to give you the eigenvalue associated to one of these eigenvectors, n. It's going to give you that integer, right? Sorry, excuse me. It's going to give you n squared. But if you measure the momentum is going to give you n. So e to the I theta is one of the states with energy 1. And e to the minus I theta is another state, which is different from the first state. In fact, it's orthogonal to it. So we have 2 distinct orthogonal states, a 2-dimensional space of states of energy 1. This is called degeneracy. It's a degenerate energy level because there are 2 states with the same energy. Okay, so if you say that this system has a certain energy, energy 1, what state is it in? Well, it's going to be in e to the I theta, or it's going to be in e to the minus I theta, or a linear combination of those. And that's a 2-dimensional state space. And so that means that geometrically, that is going to be a point on the Riemann sphere. So a particle on the circle with energy 1 is going to be a point on this Riemann sphere. That's the quantum state. The quantum state of energy equals 1 particle lies on CP1. Okay, and this is true. This degeneracy persists in, as if 2 is a square. Yeah, great. The next energy will be much higher. It will be energy 4. And there's going to be a degeneracy there too. There's exactly two states. One which is moving one way and one which is moving the other way. That's the classical interpretation because the momenta have different signs for these 2 states. So these are distinguished by P, but not by E. So what you get out of E is only the energy level, and those are degenerate. So you do not get a Fourier decomposition from the energy eigenstates in this example. You only get a Fourier decomposition in terms of the momentum eigenstates. I hope I didn't write something wrong. So this is a Fourier decomposition using the P eigenstates. Okay. Yeah. So anyway, this is what the system looks like, and we're going to see, all these behaviors. These are all prototypical. They occur all over the place in quantum mechanics. Okay, so I should I wasted too much time. I'm sorry. So let me just quickly explain the circuit notation. So the circuit notation, I was going to do a whole class on this, but I'll leave it until Friday. Okay. So when you see a line like this, so this means that we have C2 at this endpoint, C2 at this endpoint. These are the qubit state space, okay? And then this H is a linear map from C2 to C2. And this is called the Hadamard gate. It's the most common gate. It's a unitary operator. which is 1 over square root 2, 1, 1, 1, 1. Notice that what it does is that it takes the off state and maps it to a superposition of states, off plus on. And it takes the on state to, to 1 over square root 2 off minus on. Okay, so this is an example of a unitary operator that you can do on a qubit in actual physical space. Like in practical terms, you can set up an experiment where you take a particle that has 2 quantum states, on and off, and you can send it through an apparatus which will do this unitary operation to it by interacting with it. That interaction could be electromagnetic. It could be using a different force. There's many different ways you could do it. It's not important for us. The point is that we can treat this as a wire, like as a circuit, right? Where the wire goes in, it feeds the particle, which is in some kind of superposition of 0 and 1. It operates on it by unitary operators, and it spits out another state of the qubit. Okay, and then when I put these together, let's call this like U1 or U2. Okay, a diagram like this means that at the input is C2 tensor C2. So I have now 2 separate systems, right, which I'm combining, the system number 1 and system number 2. Okay, and I'm considering it to be a joint system, and this system is giving us an output, which is also C2 tensor C2, and there's some kind of unitary operator. In this case, it is U1 tensor U2, like what we discussed before. Okay. Now, okay, now, so the next thing I need to explain, I just need to explain a couple of things, and then you'll be able to do the assignment question, or you could just look up these things. They're pretty standard. They're all on Wikipedia. So we can consider 2-qubit gates or operations. So these are operations which are not, strictly speaking, just, they're not separate operations on the first and on the second qubit, but they're joint operations. So maybe the most important one is what's called controlled NOT, a controlled NOT gate. Okay, and so it goes from, the diagram is like this. This is the control. So the control, when there's a control, it means that one of the inputs is sent through the system without change. And that's your control. That's the thing that doesn't change during the experiment. So whereas the other one undergoes an operation which depends upon the value of the control. So the idea is that, so from a classical point of view, what this thing does is it flips the second bit if the control is 1 and does nothing if the control is 0. Okay. So if I write this if I write this as in the following way, this is kind of like a shorthand. You imagine that there's some state being fed in, and there's another state being fed in on the two lines. This really means that we're sending in x tensor y, where x and y can be 0 or 1, okay? And we're feeding that through. And where does it get sent? Well, x should be unchanged in the classical sense, but y will change depending on the value of x. So if the value of x is 0, it should be sent to y. But if the value of x is 1, the value of y should be flipped. But we can flip it by just adding the value of x to it, and that will achieve the same end. So that means that at least we know what this unitary operator is going to do to decomposable states. So this is a decomposable state. Okay, and by definition, it gets sent to x tensor y plus x. That's what this diagram means. It's just notation for this. Okay, but the cool thing, so if you look at this, right, if a classical electrical engineer looks at this, then they just recognize this as the controlled not operation, that depending on the value of the control, you either do the not or you don't. But the cool thing is that now we can consider non-decomposable states, or we can consider inputs which are not eigenstates. So change the input to, let's say, a general value of the control. So let's say I put the control to be something which is not in an eigenstate. Okay, so this is still a decomposable state, but it's not written as an it's not made of eigenstates purely. It's a superposition of eigenstates. And what's going to happen is that I'm going to get a superposition of the possible results, right? I mean, if x is 0, then I get 0 tensor 0. If it's 1, then I get 1 tensor 1. So as a result, what I'm going to get is alpha times 0, 0 plus beta 1, 1. So you see that this thing, what it does is it gives us an entangled state. Okay, even if the input is not an entangled state. This is the kind of crazy thing, non-entangled. Okay, so what this means is that, and you know, by the way, the controlled not is physically doable with actual apparatus. So there's no problem in doing controlled not. You can look up how they set up the experiment, but the point is that even if the input is in a decomposable state that you prepared by preparing each of the wires separately, right? You prepared your input particles. At the output, you're getting an entangled state. And that means that you have left that very thin region of decomposable states. And you've now, with your computer, you're now moving by a unitary operator, you're moving your state into this vast space of non-decomposable states. This is the power of quantum computing. It's because you can move away from the classical states and you can start operating in this larger space. Let's see, what other good one? Okay, and so the final thing that I'll say, sorry for going over, this is how an arbitrary classical Boolean function, okay, so this is just a function from z mod 2z to the n to z mod 2z to the m. This is this is what classical computation is all about. It's about binary functions. It's about things that take an input bit string to an output bit string. Okay. This is how an arbitrary classical Boolean function, this is what usual computers compute such functions. You give them an input and it gives you an output. That's what a classical computer does. So this is how an arbitrary classical Boolean function is upgraded to a unitary operator. And that unitary operator looks like this, that we have C2 to the n, which will serve as our control, C2 to the m, going to C2 to the n, tensor C2 to the m. So we have our quantum system, which is n copies. So we need n bits, n qubits to capture the input, and we need m qubits to capture the output. But we want to do this thing in a controlled way. So we want to consider like the n input values will occur in the output as well. Sorry. And the way that it will work is that it will take a classical input. So this is just like, 0, 1, 0, 0, 1, 0, something like that. So in other words, it's in an eigenstate. It's just a classical switch, a set of n switches, which I'll denote by x vector, tensor y vector, and it will send it to, the control will be unchanged, and the value will be y plus f of x. Here's our classical function. Okay, and we are defining, so what have we done now? So what we've done is we use the classical function to tell where the basis is sent. So you see that these are just the basis elements. We take a basis for C2 to the n and a basis for C2 to the m, and then we tensor them together. This is just a basis element, and the basis element is sent to another basis element of this big, huge vector space. And now that we know how the basis element goes, right, then automatically we get a linear transformation, which is the quantum operator. Why is it unitary? Because all these vectors have unit norm. These are orthonormal bases, and so we get a unitary operator. And this operator is called UF, which goes from C2 to the n, tensor C2 to the m to itself. Okay. Right. Okay. So that's all I wanted to say. We'll go over this in more detail on Friday, but basically it's just a graphical notation for writing down unitary matrices from a tensor product of C2 to a tensor product of C2. That's all that it is. So if we look, let me just take a look at the assignment to make sure. Yeah, so in the assignment, there's a picture that looks like this. There's a control here, and then an H after. And then there's a UF here. and like this. So this is an example of what the thing does. So we have, you can split it up vertically. So you can you can just consider this part, you can consider this part, and you can consider this part.
Sorry, Professor, I don't think we see what you're drawing.
Oh,
There, yeah.
yeah, sorry. So I drew the circuit in a simplified way, and now I'm just looking at it step by step. You can just put vertical lines to see how the computation goes. The computation goes this way from left to right. Okay, and each step is going to be from C2 squared to C2 squared. Okay, and it's a composition of a few different things. So in the first step, you just have this H tensor the identity, where H is, remember, 1 over square root 2, 1, 1, 1 minus 1. This is acting only on this two-dimensional input. Don't get confused by the fact that there's two streams here. This is a C2 just for this stream, and this is a C2 for this stream. Okay, and we see that the H is acting only on the first stream. Okay, then and then we have this controlled controlled application of the classical function. So we, it's given by this expression here, this. On a basis, that's how it is. That's how it works. Okay, and then the output of that is sent through another one of these Hadamard gates, and then we end up with the result. So that's what this is. Whenever you have a quantum circuit, usually the way that it will look is that there's going to be a certain number of horizontal lines. That's how you begin your computation. That tells you the dimension of your Hilbert space, 2 to the however many lines there are. So in like at Google, they did something with, I forget now, something like 20 qubits, 30 qubits, 32 qubits. So it's 2 to the power 32 dimensional space. And you have each vertical piece, each vertical segment is a unitary operator on that space. But the cool thing about that unitary operator is that it's built up from little pieces like this Hadamard gate and like this controlled application of a classical function. Okay, I'm gonna wait for questions now.
Vector addition in F to the N, that's the same, that's normal vector addition.
Could you explain what do you mean?
Sorry, in the exercise it says where the addition is vector addition in F2 to the M. That's normal vector addition, right? Or is there something special? In the instructions on exercise 5, when you're defining U to the UF?
Yeah. So like think about what I did here. You see, I wanted a controlled knot. So that means I want to flip this. I want to flip the value of y if x is non-zero, and I want to do nothing to y if x is 0. So there's two possibilities for x. It could either be 0 or 1. If x is 0, then it doesn't do anything to y. If it's equal to 1, then I'm going to have y plus 1. But what is y plus 1? I mean, y could either be 0 or 1. So if it's 0, then it goes to 1. If it's 1, it goes to 0. Okay, because this is the Boolean logic, right? We're talking about just values are possible 0 and 1. 1 plus 1 is 0. So you can describe the not operation as just addition in F2 or Z mod 2Z or however you want to call the modular integers with only 2 values, 0 and 1. If something is confusing, I could explain. I don't mind. I'm just assuming that you've seen things like Z mod 2Z, modular arithmetic, or Boolean numbers.
I have a quick question about the control gate.
Yeah.
Wait, Neo raised his hand. Well, I'll just ask, it should be quick. No measurement actually happens during the control knot, right? Because, I mean, from a classical perspective.
This is a unitary operator.
Right.
Okay, which acts on the from the Hilbert space to itself, and there's no measurement happening. Remember that measurement involves, measurement involves a projection operator, right? So that means that some vector can be sent to 0 under projection. So projection is not a unitary operator. Projection is not unitary evolution. So usually what happens is that measurement happens at the very end of the computation. If at all, if you do the measurement at all. So the idea is that you want to do some quantum computation, which is a sequence of unitary operators, and you want to end up with a quantum state at the end, which, when you measure it, anytime you measure it, it's going to be probabilistic in nature, right? The answer. But what you want is that even though it's probabilistic, you want the computation to arrange that state by that unitary transformation in such a way that the measurement will tell you some kind of information. And we're going to do some examples of that on Friday. But the idea is that you want to do that computation to move that state into such a place, so that when you do measure it, maybe what you'll find is that there's a probabilistic result, but the probabilistic result only ranges within a certain subset of possible results. And so you're like, well, I'm getting this probabilistic result, but it seems to be only distributed in a certain region, which means that with high probability, that state does not lie in that subspace. And so you can be, you can have certain certainty, like you can even arrange it so that you can be certain that it's not in a specific state. So yeah, you have to be very clever to design the algorithm in such a way that the resulting state still gives you information after measurement.
That's what the homework problem is about with the...
Yeah, exactly. Yeah, it's a very tricky subject.
I have a question that is a little bit more general. So for question 6 and 7, oh, can you hear me?
Yeah, I can hear you.
Oh,
yeah.
Okay, perfect. I was just wondering if I froze. So for question 6 and 7, after you've done all the computation, you get the formulas and numbers, we're asked about sort of thinking philosophically about the nonsensical equations that we just got. What's some, in general, for these types of situations where you try to understand something from the equations, like how do you go about the thought process that makes this more effective? And
can you give me an example? Which one exactly?
For example, let's say exercise 6, question 5. So compare these last 3 results. You'll look at the numbers you get and how are these things related? What's some good thought process that you can go through to say something genuinely interesting about about these things?
Listen, so there is no mystery here. So what's going to happen is that you know, it all depends. This is, it's all just computation. And the question is if you do the computations correctly. So if you do the computations correctly, you will be faced with some kind of obvious problem, some obvious difference, right? So it's like, if you do the computation, then you'll see that, what I'm trying to set up for you is a pair of contrasting situations. One of them is that you start with a pair of particles, a 2-particle state system, which is in an entangled state, and you make some measurements. So roughly speaking, when we think of an entangled state, you think that somehow they're mixed together in some way, like the being in state 0 and being in state 1 are somehow mixed together. Okay, but that's not really what entanglement is. Entanglement is a particular type of state of a multi-particle state, right? It has nothing to do, it's not really about superposition of two states. A single switch, a single light switch can be in a superposition of being on and off. And that has a probabilistic impact on measurements, right? So if you walk into the room and look at the light switch, it could be on or off with some probability, right? And so that's giving you some kind of ambiguity about the state of the light switch.
Mhm.
But when you have two light switches and they're in entangled state, right? What does that really mean? It doesn't mean that it means that there is some kind of yeah. So the question is like this: that being in an entangled state has some probabilistic impact when you make measurements. How do you figure out what that impact is? You make a computation. You measure an observable. I mean, you compute these projection operators in quantum mechanics, right? You prepare a entangled state, and then you apply a measurement operator to it, and you compute the probability of getting this eigenvalue and so on, right? So you prepare your entangled state, and you get a probabilistic impact. So the question is really about, is there any classical probabilistic system that has that impact, that same impact, right? So if you were a classical probabilist, how would you set up a probability experiment which would have the same probabilistic answer as what this entangled state provides? You see what I'm saying? Like, quantum mechanics is some kind of mathematical model that produces some outcomes which are probabilistic outcomes. Now, probability theory is a mathematical model that also gives the same thing. It gives you probabilistic outcomes of experiments, right? But the starting point is different for both. The starting point for a probabilist would be, let's say that you're on a game show and you have two possible answers to give, and there's a certain probability that you get a prize. And if you do this 100,000 times, what's the probability that you're going to be this rich or something, right? That's the type of initial condition that probability theory gives you the answer for. Okay, and here it would be different. It would be like, prepare yourself in a superposition of saying, like, I'm going to play the game show twice, right? And I'm going to I don't know, you could imagine certain things. You could imagine, setting yourself up in an entangled state to begin with, and then to proceed in a unitary way. And then at the end, you measure how rich you are to find out your expected winnings for some kind of quantum version of the game, right? And so this is what I mean, that you have to try to imagine, like, is there a classical analog, some process like flipping a coin or something that gives the same type of behavior? Because if you can, then there's no point of having quantum mechanics.
I see. So in some sense, the quantum superposition is in some sense more fundamental than classical probability.
Yeah, it produces you certain, that's right. And especially this, it's again, it's not so much the superposition, it's more the entanglement. It's the behavior of different, of conjoined systems. Because remember that conjoined systems, they operate, they live in a vastly larger space. And that probability theory is happening in that larger space. The quantum mechanical probability theory is happening in a massive, much larger space. And so the kind of, that's, I think, that's where you get this power from.
But conversely, the classical probability can always be modeled by the quantum stuff.
Yeah,
The other way
that's
around.
true. And you know, I mean, well, yeah, I mean, from a purely practical point of view, you could say that any quantum circuit can be modeled on a classical computer. Of course, I mean, that's what you're doing. You're presumably you are a classical computer and you're doing quantum mechanics, so you can do it. But the point is that it's you know, the way that yeah, the way that the modeling happens is in a more complicated way. I mean, you kind of you have some macroscopic system which is encoding, you know, your quantum Hilbert space, right? I mean, the way that we do quantum computations in usual computers is that we use our kind of macroscopic hard disk type memory, RAM memory, in order to encode tuples of real numbers or complex numbers, which are supposed to be a single point in a quantum Hilbert space, right? So it's like we're modeling it using macroscopic technology. Anyway, I'm sure this is not what you were asking about. I'm just trying to confuse you so that you just go back and do the assignment.
Oh, that's all good.
On Friday.
Yeah, I'm just continually thinking about the heuristic kind of question.
For exercise 7, this is another issue that yeah. So assignment exercise 7 is kind of highlighting a fundamental. It's basically explaining, okay, a fundamental fact about quantum mechanics, which is that the fact that the observables do not commute in general, that impacts probability in a very significant way. And you know, if everything in if all the observables in quantum mechanics commuted, if all of them commuted with each other, that means that they would all have simultaneous eigenvalues, and that would mean that you could imagine that your state was in an eigenvalue, common eigenvalue for all the operators, right? And then nothing would happen. Everything would proceed without changing the state, and it would just you would just have a very simple evolution. And you know, it doesn't matter if you measure one thing or another thing, or you could measure anything you want. It'll just collapse it exactly to that state, right? If you're in an eigenstate for all the available operators, that means that anytime you measure any one of those observables, you'll get exactly that eigenvalue, whatever the eigenvalue is for that observable. And there's going to be a projection operator which does nothing. So somehow the fact that different observables don't commute, that is what brings new probabilistic behavior. And this thing about standard deviations is the most important of all of those probabilistic impact. It's basically telling you that there is a lower bound on the there's basically a lower bound to the precision of your measurement of two non-commuting observables. That quantum mechanics, the fact that they don't commute, it means that there is a hard lower bound to how precisely that you could measure something. I won't go any further than that, but let's just leave it at that. It's a very famous statement, but it's all to do with the fact that the operators do not commute. Okay, so you can see there, the final equation is one of the most important equations in quantum mechanics. It's telling you that the commutator between two observables gives you a lower bound, right? So the failure to commute is what drives uncertainty in measurement.
Sounds good. Thank you very much.
You're welcome.
Sorry, just to double check, when we're multiplying, so for example, in the exercise, we need to multiply UF times UG. Is that like how would it work to multiply between tensors? Is it just another tensor, or?
UF is a unitary operator on V, not V, on V to the N, V tensor N, tensor V tensor M, right? So that's a very large vector space, and UF is a unitary matrix on that big vector space. It's a unitary operator. And what's written there underneath the first displayed equation in exercise 5, that equation is telling you what UF does to unit vector, to a basis of that vector space. So it's defining the operator because I'm telling you what it's doing to a basis. Okay, so it's an operator. It's a linear transformation from the vector space W to itself. So what does it mean? UF, UG. It means you compose the matrices. So the unitary matrices form a group, and so you'll get another unitary matrix. Is that clear, or?
Yeah, I think that's clear. Thank you.
Incidentally, you should look at that expression and you should be able to tell why it's invertible. Unitary matrices are always invertible. They form a group. But the question is, why is it invertible? Why is it that if I tell you x and y plus f of x, why can you recover x and y? I mean, it's obvious why you can reconstruct x, because x is provided to you. It's a control, right? So if you know the result of the transformation, you will know x and you'll know y plus f of x. So that means you'll know x, but will you know y? Well, y is not being given to you. What's being given to you is y plus f of x. But since you know x, then you can just compute f of x and subtract that off from that quantity and get y back again. So you can see the reason why we need that control. The control bit is there because it ensures that the transformation is unitary, that it's invertible. So it's kind of accountants would understand this. Accountants know that every single time you make a transaction, you should write down a line in the ledger, and you should always remember, in and out, and there's even this double 2-column accounting and so on, so that you can always go back and trace every transaction, right? So if you only told me if you told me that y gets sent to y plus f of x or something like this, and you didn't remember the input of your function, because in classical computation, this is done all the time, right? The ultimate idea, what computer scientists claim that we should be doing is we should be writing programs so that you know what the input is supposed to be and you know what the output is supposed to be, so that you could treat the program as a black box. And then if you give me another program which has the correct type of input, then you could just compose the two programs and make bigger programs, in this way, by composing programs that were written by other people. And because they were so careful to make sure that the input is the input and the output is the output, then that means that no program ever has to be rewritten more than once, right? That as soon as we've written one function properly with the correct input and the correct output, then we never have to write it again. So and that works real great in practice. I.e., it works not at all. That computer scientists, computer engineers still haven't figured out how to write a computer program. But in quantum computing, you always remember your input, usually, because you want it to be invertible. You want everything to be reversible, right? So reversible computing is a valuable idea even in classical computation. That you should always well, I mean, for practical reasons, you don't want to do this in reality, but it's a nice idea to express every program as a reversible program. And any program can be made into a reversible program using this idea, because you just remember the input. How hard is that, right? You just always remember the input, and then you'll always know what the input was. I would love it if the government actually got involved in regulating computer programming, so that when you let programming out into the world, that it has to be done in a modular way, so that it can be concatenated. That would be so great. It's like parts, right? It's like certified parts, certified quality control by an external certification agency. I guess they do have that. There are companies who do that. But I mean, when we have computer programs running our buses and our cars, I think there's a role for government to play to regulate computer programs. It's not, it's not even it actually would be good for them. They should welcome such a thing. Oh man, getting off on tangents. I think the Zoom thing, it really makes me go off on tangents. In class, I don't ever do this, but the Zoom thing, it's because I'm at home and I feel comfortable, so I start talking all kinds of nonsense. And it's even being recorded. I have to stop the recording.
So if no one else has a question, could you help explain a little bit?
I didn't record.
Sorry?
Oh,